So this is my worked solutions for the A2 Pure 3 paper for the O3 region that was done in October 2018. But one thing that you need to bear in mind is that I've worked through this before the mark scheme is available. So these are my best solutions, and there could be mistakes in them. If you find one, please just pop it in the comments and I will put corrections in the description for the video. So just check on the description underneath and you'll be able to see if there's any corrections that need to be made. So question 1 gives us a fairly straightforward modulus question to have a look at. First thing you should do is try to draw a graph of what this looks like. Now I say it's fairly straightforward, but of course this is A2 maths, so they've given us an A to think about there rather than actual numbers to be able to plot it. So just think about your y-axis in terms of A. So if this was A, 2A, 3A, and so on, and then you can have a think about what that would look like. So the first one we'll plot will be the one that's the 2 modulus 2x minus A. So this will have a fairly steep gradient because it's got that 2x and then it then also gets multiplied by 2. So we're looking at a gradient of about 4, and it would go through the y-axis. If it didn't have the modulus involved in it, it would go through at minus 2a. But of course it gets reflected up, so it goes through at positive 2a with a fairly steep gradient. Now the other one, x plus 3a, maybe we should have started with that because it's a little easier to think about. We are going to do x plus some constant. This is the constant 3a. So it goes through at 3a with a gradient of 1. So it's a shallower gradient than we had before. Something like this. Oops, let me do that again. Okay, and so now we can see where we're looking for solutions. So the points of intersection are here and here. So we're going to find those points first of all, and then we will work out what to do with this inequality that we've got. Right, so if we start off with this one here, that one occurs when you have the positive section of both of those modulus graphs. So that will be when we have 2 times 2x minus a equals x plus 3a. So work that through and you get 5a minus 3. Sorry, 5a over 3. The second point here happens when this modulus here, the x plus 3a, is positive, but this modulus, the 2 one, is in its negative part. Is when it's got reflected over. So that point of intersection will happen when we have 2 times negative 2x plus a. So the negative of what was in that modulus is equal to x plus 3a. And if you work that through, you get x is minus a over 5. So then the next thing to figure out is the inequality. So we want to know when this inequality on the left-hand side is less than the inequality on the right one. So when that graph, that steeper graph that we drew, dips below that shallower graph. So we're looking at this portion here, and that happens in between the 2 values that we just worked out here. So then our inequality needs to go in between those 2 values. Question 2 is testing you on logs and exponentials, and we're going to solve this equation. So first of all, we'll do a bit of rearranging, and from there bring everything over to one side. So I'm going to move everything over to the right hand side, and that becomes 2e to the x minus 5e to the minus x equals 0. Now take out a factor of e to the x, and we can solve each part of that. So e to the x can't be 0 itself, so we must have that what was in the brackets is equal to 0. And carrying on from there, I'm going to have to just move up. We get to e to 2x equals 5 over 2. So if we take log of both sides, we get 2x equals log 5 over 2. that x is half log 5 over 2 and pop that into your calculator, and you get 0.46, and we're specifically asked to do it to 2 decimal places, so that's where we'll stop. Question 3, we are going to sketch the graphs of each of these. So first we're going to sketch y equals x cubed. And then y equals 3 minus x. And from that sketch we can show that there is one point of intersection, which means that there will be exactly one real root. Part 2, we want to show that this iterative formula is equivalent to the equation we were given before. And just a reminder, that equation was x cubed equals 3 minus x. I want to show that it's the same. So we'll start by writing the iterative formula just without its iterative parts of it, so that n plus 1 stuff, and we'll work through rearranging that. Okay, so you can see we get to the formula we were looking for. We just need to finish it off with a statement. Now we need to use that iterative formula. Choose a sensible starting place. Now if you look at the sketch that you did, you can see our root is somewhat close to 3, and we'll go from there. So if we start with our initial term being 3 and put that into the iterative formula like so, you get the first, so the x1 value 2.03571, and you carry on, you put that into the next one, and so on. Remember to put each of your answers to 5 decimal places as requested in the question, and we need to produce as many of them as necessary to be sure of the answer to 3 decimal places. So with parametric equations, we first of all need to work out dy by d theta and dx by d theta. So dy by d theta, if we differentiate that y according to theta, we will get minus 2 sine theta minus 2 sine 2 theta. Similarly for dx by d theta. And then dy by d theta, not d theta, dy by dx will then be dy by d theta multiplied by d theta by dx. There's no need to try and simplify it at this point, we haven't been asked to. Part 2 is slightly unusual because they're asking us to find the point on the curve where the tangent's parallel to the y-axis, and a lot of the time we're asked for it parallel to the x-axis. Y-axis means it's going straight up, which gives it an infinite gradient, and that will happen when your denominator equals 0. So when you try to divide by 0 and it just kind of breaks. So we're going to set that bottom part of our dy by dx equal to 0. And carry on through and solve that. So working that through gets us down to cos theta equals half and cos theta equals minus 1. Now the cos theta equals minus 1 is actually not within the range that we've been given in the question, so we will ignore that one. If you look back to the beginning of the question, it told us that theta needed to be between 0 and pi. So that's not going to give us an answer in that range. So carry on with cos theta equals a half, and we get theta equals pi by 3. So this question, we're going to need to use separating variables. So we bring all the y's over to one side, so we get 1 over y dy, and all the x's over to the other side, so this becomes 2 minus x squared over x dx, then we're going to integrate the both of those. So just going to tidy up this 2 minus x squared over x into being 2 over x and then minus x, so just separating that fraction out into its two parts so that we can integrate that. Then integrating each side of that, we get log y on the left hand side. 2 over x becomes 2 log x, and x is x squared over 2 plus some constant c. Now we also know that when x is 1, y is also 1. So working that through gives us a constant of half. So pop that back into the equation that we worked out above, and we've got log y is 2 log x minus x squared over 2 plus a half. Now we need to get this in terms of y. I'm just going to come up to the other side over there. So we will have, if we raise everything to the power of e, we'll get the y on the left hand side, and then we get e to the power of 2 log x minus x squared over 2 plus half. We've got to try tidy that up. So that'll look like this. So I get my final answer to be this. I have a feeling there might be a more elegant solution, but that's my best go at it. So we've got a trig equation here, and we need to change it into a different form. So first of all, let's just started out by writing that equation instead of cosec and cot as the fractions that they are, so we can see what's going on. So we can see we've got sine x on the bottom of both of these fractions. So if we combine that to have that common denominator of sine x, it'll be root 2 plus cos x on the top, and that equals root 3. So then rearranging that, we get that root 2 equals root 3 sine x minus cos x. And now this is in a more familiar form for us to be able to change it into that r sine x minus alpha that we're being asked for. Now remember, this is all to do with triangles, and r is to do with, r is the length of that hypotenuse. Our coefficient of cos is 1, and of sine is root 3. So we carry on with that, and we get that r will be root 3 squared plus 1 squared, which is the square root of 4, and that gives us r is 2. Tan theta is 1 over root 3, so theta must be 30 degrees, and just double check that whether you're in degrees or radians. So then put that back into the form that we're being asked for, and we get 2 sine x minus 30 degrees equals root 2. So now we take that equation that we just worked out, which was this one, and we're going to solve that because we know that that's equivalent to the equation we're being asked to solve. So if I carry on with that, we get the following. Right, with this one, I know I'm going to run out of room, so I'm going to start writing my answer just up at the top left corner over the white portion there. Obviously you would set this out with plenty of space. So first of all, we are finding the x-coordinate of m, so it's the position of that turning point. So we need to differentiate, set it equal to 0 and find the solutions. So to differentiate that curve, if we set u as being 5 sine squared x, which I'm going to write like this, it just helps me to see what I'm doing, then du by dx will be 10 sine x cos x. V would be cos cubed x, which would be cos x all cubed, so we can see what's going on there, and dv by dx is equal to minus 3 cos squared x sine x. Then we put that together using the product rule so that we get dy by dx. Next we need to set that equal to 0, and I'm going to factorise out 5 cos squared x from that at the same time. Then we take each portion of that and consider if we set it equal to 0 what the solutions would be. So working through, if 5 cos squared x was equal to 0, that would give us a solution of x equals pi by 2. That is clearly not m. A quick look at the graph would just show us that that's not where m is, that's where the bottom of that bump is. So now we consider the other part being equal to 0, and we work that through to get the following. So from that blue portion of working out, we get that either sine x equals 0, or 2 minus sine squared x will equal 0. So if we work through sine x equals 0, that would give us x is equal to 0, which of course it can't be. Or rather, it's not the solution we're looking for. That's not m, because x being equal to 0 would be at the beginning of the graph. That's not where m is. So carry on with the 2 minus sine squared x equals 0 gives us that sine squared x would be 5 over 2. So sine x is the square root of 5 over 2, and if you do the inverse sine of that, you get that x equals 0.65. That is our x coordinate of m. So we are told to use the substitution u equals sine x, so that's a nice handy hint to find the exact area, which means we're integrating that curve between 0 and pi by 2. So if u is sine x, du by dx will be minus cos x, which gives us dx is equal to minus 1 over cos x du. Okay, substituting back into the integration, we then get our limits change slightly. So if we are turning 0 and pi by 2 into their values in terms of u, we just stick that into the u equals sine x. So sine of 0 is 0 and sine of pi by 2 is 1. Sine squared x becomes u squared, so we get 5u squared. Now the cos cubed x we'll leave there for a second, and we multiply that by minus 1 over cos x du. So replacing the dx with its equivalent. So that simplifies down to cos squared. And the cos squared we can use 1 minus sine squared and get everything in terms of u. And then we go ahead and complete that integration. So we get 5u squared becomes minus 5u cubed over 3, and the plus 5u to the power of 4 becomes u to the 5, and we will use the limits of 0 and 1. Which gives us our final answer is that the area is 2/3.
So we need to be able to work out the modulus and argument to put it in the form re to the I theta. First of all, we're just going to sort out what's going on with this fraction. So we've got our complex number stated like this. We need to multiply it by the argument of the denominator. And we get minus 4/5 plus 7/5 I. Now have a think about what that looks like on an Argand diagram. It will of course be over in this quadrant here, where we are up at 7/5 I and along at minus 4/5. Okay, now the argument is always the angle made with the positive x-axis. So this here is the theta that we're looking for, which makes this angle here pi minus theta. Now pi minus theta we can work out by looking at this triangle. So tan of pi minus theta will be 7/5 divided by 4/5, making pi minus theta 1.05165 radians. So theta then turns out to be 2.09 to 3 significant figures. R is the modulus, so that's the square root of 7/5 squared plus 4/5 squared, which comes to 1.61. Therefore, our complex number is 1.61 e to the 2.09 I. For part B, we need a strong understanding of the geometry of complex numbers and their loci. So this first thing that we're taught about z, if we rewrite that as z minus a complex number like this, then that's telling us that from that complex number to z we'll have a length of 1. So that's going to give us a circle. So that complex number will be in the bottom right quadrant. So I'm just going to draw that section of the Gann diagram. So that will be around about here with 3 along and minus 2i. So if we have the distance that z can be from that point is always 1, we're going to have a circle with radius 1 centered on that complex number. And it always helps to write down the details of what it is you're trying to sketch in case your drawing is not that fabulous. Okay, now find the least value of the modulus of z for the points on this locus. So we want the shortest distance that z could be from the origin. So z can be anywhere on that circle. The shortest point will be when it's over, like on this line here towards the circle. So it's wherever it would touch the edge of the circle there. Now we can find the length of that line that I've marked in red because that is the modulus of the complex number 3 minus 2i. So that comes to the square root of 13. Now to get to this point on the edge of the circle here, that will be our z value with the least value of the modulus of z. So that point from the origin, so that I'm marking in blue now, that distance will be as far as to the 3 minus 2i, but subtract this radius. Now that radius is equal to 1. So therefore, the modulus of z will be square root of 13 minus 1. And we want to express that that's the smallest that the modulus of z can be. So let's just turn that into a greater than or equal to. And just to be sure, we'll write it as a sentence that the least value of the modulus of z is root 13 minus 1. And note in the question we had to leave it in exact form, so don't turn that into a decimal. So expressing in partial fractions, we'll need the arrangement that I've written there in blue. And with that, we get the top line will be equal to the following. Now, if we take the value of x equals 2, that will get rid of the brackets where we've got 2 minus x. So on the left-hand side, we will have a value of 49, and on the right-hand side, we will have 49a, which tells us that a must be 1. Now, you can do this in any order you like. There are other ways to solve it as well. This is just the order I'm going through. So next, I'm going to compare the x squared terms. So on the left, we have 6. And on the right, we have 4a minus 2b. Now we know that a was 1, so we get 2 is minus 2b, so b is minus 1. Next, I will compare the constant terms. So on the left, we have 9, on the right, 9a plus 6b plus 2c. Now we already know what a and b are, so we can pop those in. We get 2c equals 6, so c equals 3. So then f of x equals, and just finish that off with the values of those terms a, b, and c. So for part 2, we need to use that partial fraction we just worked out in the first part to be able to do this integration of f of x. And this gets into some pretty hideous log rules that you've got to be very careful about. I'm going to take this one step at a time and I'm going to deal with each fraction individually. So our first one, if you integrate that, you get negative log 2 minus x. The next one is half log mod 3 plus 2x. And the other one is by inspection or reverse chain rule. You might just need to do a little bit of working out at the side for this one. Is 3 over 2 brackets 3 plus 2x. And substituting in the values, we get the following. And then we have some tidying up to do. So we've got minus log 2 plus log 3. It's going to give us log of 3 over 2, because if you subtract the logs, it gives you a division inside of them. Then we take away. Now log 1 is 0, so on this one we're just left with half log 3. And then over here those fractions cancel down to 1, which is looking promising because we've got the 1 that we want. The rest, to get the half log 3/4, there might be easier ways to this, but it's a little bit of fiddling around until you get what you need on this one. So for log of 3 over 2, if you turn that into 9 over 4 and then to the power of a half, because then the square root of 9 over 4 would give you 3 over 2, and you subtract that half log 3 plus 1 is still there, then we can rewrite that as half log 9 over 4 minus half log 3 plus 1. We can take out that factor of a half, so then it's 9 over 4 divided by 3, because we've got the subtraction and we've taken out the factor of the half, which then gives us half log 9 over 4 divided by 3 is, of course, 3/4 plus 1, which is what you are asked to do. That brings us to our vectors question, which has two very nice first parts to it and a slightly trickier third part. So first of all, we're showing that L is parallel to M. That means there will be no points of intersection. So we try to find those points of intersection and then show that that doesn't work and there are none. So we've got the equation of the line and of the plane. Now that equation of the line we can put together and make it 4 plus lambda, 2 plus lambda, 1 plus 2 lambda, and then put each of those in for x, y, and z in the equation of the plane, which gives us 3, 4 plus lambda, plus 2 plus lambda, minus 2, 1 plus 2 lambda will equal 10, and then we try and solve it to work out what lambda must be. So our next line gives us 12 plus 3 lambda, plus 2 plus lambda minus 2 minus 4 lambda equals 10. And if you simplify that, you get the lambdas all cancel. The numbers on the left hand side come to 12, and that's telling us 12 equals 10. This is not possible. So therefore there are no points of intersection and L must be parallel to M. Okay, so the acute angle between the planes will be the same as the angle between their normals. So we're going to use the scalar product to find that. So the normals to the two planes are the vector given by the coefficients from their equations. I'm being slightly lazy in my notation for the scalar product. Over there I'm using m and n to refer to the equation, the vectors for the normals rather than the equation of the planes themselves. Okay, we'll carry on from there. So we'll do the scalar product first, and that comes to minus 3. Then the modulus of each of those vectors. So the modulus for the normal to m, that's root 14. And similarly for the modulus of the normal to n, which is 3. So now if we put that into the scalar product, so cos theta will be minus 3 over 3 root 14, which gives us theta being 105.5 degrees, but we are being specifically asked for the acute angle, so acute from that theta will be to take 180 minus that value of theta we worked out, so that's 74.5 degrees.
So this last question on the whole paper, another vectors one, part 3 of our vectors question, and it's really quite a tricky one, just to figure out exactly what you're supposed to do with it. And then once you've figured it out, there's a lot of places you can go wrong. Trust me, when I was working this out on paper, I made a lot of mistakes first. Fortunately, you can check it at the end and see if you're right or not by plugging it back into the formula for the distance from a point to a plane. But anyway, let's jump into the solution. So we've got the equation for L and the equation for N, and we're working out where P could be if it lies on L and it's a distance of 2 from the plane. So let's just have a look at what that's looking like as a picture. So we've got our plane N, and then L is a line that we don't really know exactly where it goes, but it's most likely going to go through the plane, but we don't know at what angle. Now we can have P somewhere on there, so P could be anywhere on that line, so it could be here as long as it's distance to the plane. So the perpendicular distance to the plane gives a length of 2. So P could be up here, but it could also be down here where the distance would also be 2. So P is a particular instance on that line, and we can have 2 possible solutions. So OP, giving us a position vector for P would be just some particular instance. I'm going to use T for our value of lambda at that particular instance on the line. So then we can put that in. You could use any letter you want. In fact, you could just carry on and use lambda. Just for completeness, I am replacing it with a T to show it's a particular instance of lambda. I'm going to use the formula for the distance from a point to a plane. So we have our point OP in terms of T. So now we multiply the coefficients of the plane by the parts of the vector OP. So it'll be the modulus of 1 times 4 plus T plus negative 2 times 2 plus T plus 2 times 1 plus 2T minus D, which is 5. And that will be all over the square root of those coefficients from the equation of the plane. And we're told in the question that that will equal 2. Now this bottom bit here equals 3, so just to save me a bit of room, I'm going to get rid of that now, do the rearranging of that part now. We'll do the 2 times the 3 here, so that gives us a 6. Then expanding those brackets, we get this, which tidies up to look like this. We get minus 3 plus 3t, modulus of that equals 6. That's a modulus sign there. Okay, so now we have that either minus 3 plus 3t will equal 6, or minus 3 plus 3t will equal minus 6. So that gives us values of t to be 3, or t is equal to minus 1. And then we work out what OP would be for each of those. So OP, if t was 3, we put it back into our formula up here for OP. So that's going to give us values of 7, 5, and 7. Or if t was minus 1, we get values of 3, 1, and minus 1. And you can actually check this at the end. You can take those and plug them back into the formula that you know and check that they come to 2.